Hey everyone, so in this video we're going to investigate derivatives of exponential functions. So just a couple of little things. We're going to be working with a function. Say we have f of x is equal to b to the power of x. In this case, b is going to be greater than 0, and b is also not going to be equal to 1. So this is the standard exponential function that we've worked with in the past, going back to about grade 11. Okay, now remember that this exponential function can kind of take two different forms. So it could look something like this, and this is going to be if b is greater than 1, right? So it would be an increasing exponential function, right? Or it could look something like this, and this is going to be if b is between 0 and 1. Now, what I'm going to point out to you is that no matter which of these two cases we're dealing with, it should be conceivable that we should be able to pick any random point on it and then draw a tangent. So for example, if we're looking at the one on the left, right, I've just picked a random point and I've drawn a line tangent to the function at that point. And of course, since we're able to draw a line tangent to the function at a particular point, we understand that the slope of that tangent line should be equal to some particular number. And that means that we should be able to have a derivative for this function at that particular point. Now, I picked a random point in the function, and that means that, I should, in this case, be able to do it with any other function. Again, if you take a look at it, it's a nice, well-behaved, smooth function. It looks like something that should have a derivative. And of course, on the right, we have a decreasing exponential function, and we have the same sort of scenario. If we pick any random point, it looks like we should be able to draw a tangent line there, and that tangent line, of course, is going to have a slope. And this again implies to us that we should have a derivative for this function at that point. And since I just picked a random point and it doesn't really seem like it's special in any particular way, that means that we should be able to do this for any point on the function. In other words, it seems to be the case like if f of x is equal to b to the power of x, then there should be a derivative function. So what we're going to do is we're going to take a look at what the derivative might be. So in this case, we're examining what f prime of x is. And of course, since we don't have a derivative rule for exponential functions, we're going to have to go back to first principles. So we're going to be taking the limit as h approaches 0 of f of x plus h minus f of x over h. Now, when we apply the first principles definition to the exponential function f of x equals b to the power of x, it ends up giving us something that looks like this. Limit as h approaches 0 of b to the power of x plus h minus b to the power of x over h. So what we're going to be doing with this is I'm going to get you to take a look at the term in the numerator, b to the power of x plus h. Notice that we have x plus h as an exponent. Now, I can actually split this one term, b to the power of x plus h, into two factors in the following way. So this is going to give us limit as h approaches 0 of b to the power of x times b to the power of h minus b to the power of x over h. So notice that the b to the power of x plus h term becomes b to the power of x times b to the power of h. And of course, that's just us using an exponent rule, right? Imagine if we got from the line that we're currently on and worked backwards to the one above it. All I'd be doing is b to the power of x times b to the power of h. Since these two are exponential terms with the same base, we would add the exponents, and that would get us an exponent of x plus h. Okay, well, in the numerator right now, I'm going to get you to notice that we have two terms, b to the power of x times b to the power of h, and then we have minus b to the power of x. Now, these two terms have common factors of b to the power of x, and because of that, we should be able to perform common factoring between those two terms. So pulling out the common factor of b to the power of x, that's going to give us the limit as h approaches 0 of b to the power of x times b to the power of h minus 1 all over h. Okay, so at this point, I'm going to get you to notice that b to the power of x factor that we have here, in this expression, it obviously doesn't have an h in it. And that means that what we're going to be able to do is we are going to be able to apply limit properties, right, in such a way that allows us to pull the b to the power of x out front in this way. So that's going to give us b to the power of x multiplied by the limit as h approaches 0 of b to the power of h minus 1 over h. Okay, so we're going to pause here for a moment and we're going to take a look at this because this is actually very, very important. So there's something very interesting going on here. What I'm going to point out to you is that the limit that we have here, right, that limit there, well, if you think about it, if it can be evaluated, which we imagine that it should be able to be evaluated because we know that we should have a derivative, but if it can be evaluated, right, it should be some value which is going to depend on b. So, for example, imagine that b was equal to 5. That would mean that the original function that we're dealing with is f of x is equal to 5 to the power of x. And that means that this limit that we're dealing with here would be the limit as h approaches 0 of 5 to the power of h minus 1 over h. Now, that limit should evaluate to some particular number. We don't know what that number is right now, but it does evaluate to some number. And again, that's just going to give us some number, which is going to depend on b. Now, the reason why this is important is because what you're going to notice is that in this line, since we have b to the power of x multiplied by this limit, that indicates to us that the derivative of the function f of x is going to be the function f of x itself, which is b to the power of x, multiplied by some number, which of course is going to depend on what b is. Okay, well that's interesting. So the derivative of an exponential function is just going to be some constant multiple of itself. Okay, so now what we're going to do is we're going to pretend like we're mathematicians for a moment, because what a mathematician would do at this point is a mathematician might ask themselves, well, hold on, is there a value of b that would allow this entire limit to evaluate to the number 1? And the reason why a mathematician might ask themselves that is because if there is a value of b that allows this limit to evaluate to the number 1, then that would actually mean that the derivative of that exponential function with that particular base value would be itself times 1. In other words, we would have a function that would be its own derivative, and that would be a really, really important thing. So what we're going to do, right, is we're going to see if we can find a value of b that will let this limit evaluate to the number 1. Now, unfortunately, for the purposes of our course, this limit is going to be a little bit too complicated to deal with in an algebraic or numerical way. So what we're going to be doing is we're going to be using some graphing technology. So what you should do is you should pull up any graphing calculator you like. I like to use Desmos, all right? And we are going to be plotting, right, basically the expression we're taking the limit of, which would be b to the power of h minus 1 over h. You can kind of see it up in the top left that I've typed that in. Now, in this case, the x-axis is functioning as our as our h values, rather. Okay, so it's functioning as our h values. Now, here's the thing: since we're applying the limit as h approaches 0, that means that we're going to be letting our h values, which again is like the x values here, we want the h values to approach 0 from the right and then also from the left, and we would like to achieve a value of 1. Now, what I've done is, if you notice, there's a little X mark on the y-axis there. That is where we would have a value of 1 for this limit. Now, I'm going to get you to notice, right, that we are a little bit below that value, right, with the graph that we have here. So we're a little bit below 1. Now, I'm going to point out to you that I happen to choose a value of b being equal to 2. So when we let b be equal to 2, it seems like the limit as h approaches 0 of, in this case, it'll be 2 to the power of h minus 1 over h, is going to be not quite equal to 1. It's going to be a little bit less than 1. Okay, so what we're going to do is we're going to maybe pick another value instead of b is equal to 2. So that'll be our next slide here. So let's see what we have. All right, so when we do that here, right, what we're going to notice is that, again, if we apply the limit as h approaches 0, that means we have to look at what's going on from the left and the right side of the graph. Right, I want you to notice that we, in this case, are actually a little bit above the mark. Okay, we're a little bit above 1 in this case. Now, this is what's happening when we end up getting a b value of 3. So when b was 2, the limit evaluates to something a little bit lower than 1. And then when b is 3, the limit that we're looking at is going to evaluate to something a little bit bigger than 1. And that means that we should be able to find a b value that's between 2 and 3 that will evaluate exactly to the number 1. And that's going to bring us to the next one. Okay, so in this scenario, I've put together a graph where the limit is going to evaluate to pretty much exactly the number 1. Now, it's not going to be exactly, and I'll explain why in a moment, but as you can kind of see here, it looks like it's very, very close. Anyways, looks like it passes right through that kind of marked off area. Now, that's going to happen in this scenario when the b value is approximately 2.71828. Now, that's a very, very special number. Okay, a very, very special number. In fact, it's so special that it's a constant, and we have a special name for it, which we're going to get to in a moment. But that number is approximately, right, 2.71828. That's approximately equal to some very, very special number, all right? Now, the special number that we're going to be dealing with is going to be similar to pi in the sense that it has an infinite number of decimals, right? So all we're able to do is kind of give an approximate, like a decimal approximation of the number, which is why I said it doesn't technically pass exactly through 1, but it is very close. Okay, so that number is going to be very, very special. All right, so what we're going to do is we're going to go back to where we left off, right? So here's where we left off, and we said, okay, that limit should evaluate to the number 1 for a special value of b. Okay, well, we found that special value of b. So what we're going to say is if b is equal to, well, about 2.71828, right, then that should be equal to 1. Now, by the way, that special number b that we have, 2.71828, we have a special name for it. It's called Euler's constant, and we actually have a special symbol for it. So again, when you're working with pi, you obviously use a Greek letter pi to represent it. When you're working with Euler's constant, we use just the letter e, the lowercase letter e. So that's Euler's constant, and it's approximately equal to 2.71828. Okay, so if b is equal to that very special number, then what we have is that the limit as h approaches 0 of b to the power of h minus 1 over h is exactly equal to 1. All right? Or if you prefer, the limit as h approaches 0 of e to the power of h minus 1 over h is exactly equal to 1. Now, once again, the reason why that's important is because we have found a number, right? In this case, that number is e. We have found a number so that when we take the derivative of an exponential function with that number as the base, then the derivative is exactly equal to the function that we started with. In other words, if f of x is equal to e to the power of x, where again, e is that special number, that special constant, Euler's constant. So if f of x is equal to e to the power of x, well, then f prime of x, the derivative of that function, is equal to e to the power of x. So that's actually kind of amazing. We've found a function that is its own derivative. And that means that the y values, right, of the function f of x are going to be exactly equal to the instantaneous rate of change of the function at the point under consideration. Okay, so that's kind of interesting. Now here's the thing. At the beginning of this video, we started looking at, okay, well, what's the derivative of just some random exponential function b to the power of x? Now, unfortunately, at least at this point, we don't have exactly enough information to come up with a specific derivative rule for f of x is equal to b to the power of x. That's actually going to be coming up soon, all right? Not in this video, but soon. But what we do have is we have the ability to take the derivative of this particular exponential function where the base is e, and that means that we're going to be able to combine it with some other derivative rules that we know. So let me open up another slide here, and I'm going to show you exactly what I mean. So in this scenario, imagine that we have a function g of x. In this case, g of x is going to be equal to e to the power of 2x. And remember, e is that special number, which is approximately 2.718 or so. Now, what you're going to notice is that this function looks kind of sort of like e to the power of x, all right? But it's not. It's really more like we've taken e to the power of x and have replaced the x with 2x. In other words, this is a composite function, all right? And in this scenario, the outer function, the outside function, is behaving like e to the power of x, and the inner function is just 2x. And of course, if I want to take the derivative of this function, that means that we're going to have to be using the chain rule. All right, so let's go through the motions using the chain rule on this function. So we're looking for g prime of x, and of course, if we're using the chain rule, that means that we're going to be taking the derivative of the outer function. Well, hold on, the outer function is behaving similarly to e to the power of x, so that means that we're going to have, the derivative of that function is going to be itself, like we just showed. Right? So the derivative of the outer function is just going to be e to the power of 2x. But now we need to multiply by the derivative of the inner function. Okay, well, what's the inner function again? Well, it's 2x. Okay, well, the derivative of 2x, that's just a simple linear expression. The derivative of that should just be 2. So we multiply by 2. And of course, we can clean up this function a little bit, right? If we have e to the power of 2x times 2, we can instead write it as 2 times e to the power of 2x. So this is going to be the derivative of the function g of x. Okay, let's take a look at another example. So in this scenario, let's say we have a function r of x, and let's say r of x is equal to e to the power of x squared plus 1. Okay, well, again, this is another composite function. The outer function, right, behaves like e to the power of x, but it's like I've taken that x and I've replaced it with x squared plus 1. So my inner function would be x squared plus 1. Okay, so we're going to be using the chain rule again. Chain rule says that to take the derivative of this function, we start by taking the derivative of the outer function. And since the outer function is behaving like e to the power of x, that means its derivative is going to be equal to, okay, itself multiplied by the derivative of the inner function. Okay, well, the inner function, x squared plus 1, what's the derivative of that? Well, again, that's just where we're using the power rule and so on, and that gives us 2x. Okay, so the derivative r prime of x is just going to be equal to e to the power of x squared plus 1 multiplied by 2x. And if you prefer, you could simplify that a little bit by writing that as 2x times e to the power of x squared plus 1. Okay, let's do one more. Let's suppose now that we have a function h of x, and let's say h of x is equal to e to the power of cosine of x. Okay, well again, this is a composite function. The outer function behaves like e to the power of x. The inner function is just cosine of x. So to take the derivative of h of x, so h prime of x, this is going to be equal to the derivative of the outer function, which is going to be equal to itself essentially, so e to the power of cosine of x, multiplied by the derivative of the inner function. So now we just have to remember, what's the derivative of the cosine of x? Well, that's just equal to the negative of the sine of x. And of course, we can simplify this. Right, this is just going to give us so let's see, it's going to be negative sine of x multiplied by e to the power of cosine of x. So I figured I'd just show you a couple of different examples of some functions that we can deal with here. Again, it's not the derivative of every exponential function, right? We will be dealing with that soon, but we are able to deal with the derivative of exponential functions as long as the base is e. Anyways, I hope that that's been fairly helpful. Take care.